on this computer. So I think last time we talked about how do we find a invertible matrix P such that a P inverse P is a diagonal matrix. Like I said last time, you cannot always do this because but I didn't tell you why, because for last worksheet, for every problem you can do this process. But today we are talking about the case for some matrix you cannot find a P such that P inverse AP is a diagonal matrix. So you may ask me why or when I cannot find this P. So first let's tell you a theorem. So if we have a matrix, so and then if A has an distinct eigenvalue, then you must there exists P such that P inverse A P is the eigenvalue. Okay, so means that if you have n different eigenvalues, you can always do this process, or you can say A is diagonalizable. So when we cannot find there is no general rule say for what kind of matrix you cannot diagonalize it. Okay, so but today we will encounter with this kind of case. For example, so if we have a matrix today, we are talking about this case. We have a matrix A. So you may find lambda 1, lambda 2, and lambda n. Probably some of them are the same. I don't know. But the rule is like this. For example, if lambda 1 is lambda 2, right? Or you do this, we can write it as a lambda. Okay. Like this, you try to solve this equation. If the multiplicity is 2, okay, like lambda, for example, I talk about lambda 1, lambda 2, lambda 3. For example, lambda, this is lambda 3, lambda 1 is lambda 2, but lambda 3 is different from lambda 1 and lambda 2. So if here, for of course, for lambda 3, you can only solve one. We are talking about a 3 by 3 case. So you can always find one eigenvector. But the problem is this part. If for this part, you can't find, if you can only find one eigenvalue, eigenvector, means that you cannot find enough P, because P is the alpha 1, alpha 2, alpha n, the eigenvectors. If the multiplicity lambda 1, if lambda is 2, means that if you only find one vector, so means that you cannot make up a n by n matrix. But if you solve 2 or alpha 1, alpha 2, here you have alpha 3, you can still get alpha 1, alpha 2, alpha 3. So means that in this case, you can find enough vectors to make up your P. So finally, the conclusion is like this. When is a matrix diagonalizable? The problem is that, for example, for n by n matrix, you have to find n distinct. No, of course, it's distinct. You have to find n eigenvectors For example, if you look at this theorem, we say you have to find an distinct eigenvalue, but here you have to find an eigenvector. You may, perhaps, of course, if you count the multiplicity of the eigenvalue, you always have n eigenvalues. But when you are doing your problem, for example, the eigenvalue could be 1, lambda 2 is 1, lambda 3 is 1, and lambda 4 is 2, lambda 5 is 4, like this. You can say for the eigenvalue 1, the multiplicity is 3. Of course, you only have one eigenvalue, which is 3, is 1, multiplicity is 1. By the theorem, if the multiplicity is 1, you can always find 1. For example, this alpha 4, alpha 5. You can always only find 5. Okay, only 1. For example, you can only find 1. You cannot find 2. Only 1. And but for this part, the eigenvalue is 3. But we know you can at least find 1. But I don't know. In general, you can find 2 or 3. But I can only tell you, you can find at least 1. I don't know if there is alpha 2, alpha 3. Yes, that's what I will say. So today is kind of we are doing this problem kind of, the question is, the problem is giving the eigenvalue and you try to find the eigenvector. If it's 3 by 3, you have to find 3 eigenvectors. If it's 4 by 4, you have to find 4. N by n, you have to find n eigenvectors. If you can find enough like n eigenvector, means that this matrix can be diagonalized always. Okay, this is kind of the first type of problems. Okay, what's the second type of problem? The second type of problem is like this. If we have a matrix or 2 by 2, 3 by 3, 4 by 4, nobody knows. Okay, how do we compute this? N, maybe n is big. N is 1,000, 10,000, 1 million, like that. Okay, so the problem is that you cannot just say, okay, let's multiply 1 by 1 and do it by the mathematical induction. No, in general, it's if the matrix is n by n, I don't think you have enough time to find A2, in a test, or if you may say in your homework, first you have to compute n, at least you have to know A3, A4, like that. Anyway, just forget that method. So the method is like this. In general, if the problem like this, okay, you first you find a P such that P inverse A P is some diagonalizable matrix or diagonal. Okay, after you find this, means that you can write A as this form, right? After you do this, okay, so someone is talking to me. Okay, I think this material for Thursday. Did I open the wrong one? Sorry. So let me check. Perhaps maybe I opened the wrong PDF. Okay. Wait for a moment. Okay, let's. Wait. Okay. Alt. Or perhaps because I think. Oh, perhaps. Okay, let's first finish it. Okay, I opened the wrong materials. Okay. Anyway, doesn't matter. Okay. So, and then after we do this, we can compute n like this: PDP inverse, PDP inverse, PDP inverse, like this. So you will say, okay, they cancel. each other in the middle one. So we get a P, D, N, P inverse. Okay. So anyway, I made a mistake, sorry, because Kim sent me something says, okay, this is for Thursday. Anyway, the same. Okay, let's come back to today's material. Today Tuesday. Okay, that's for Thursday. It's the same. I can talk it together. So the problem is that I think this part already had been talked on just last Thursday. So the problem is that we have like this A plus B plus C Y is something function. I think I talked about this last Thursday. Okay, so how do we solve this? The step one is solve the homogeneous equation. Cy is 0. I think how do we solve it? The method is called OIN method. You find the characteristic. You try to solve A lambda squared plus B lambda plus C is 0. You try to solve lambda 1, lambda 2, and then there are many cases. So real roots, complex roots. I will not repeat the part. After you find the solution, this is called Yx. And then for some special Fx, you have to, remember the table in the lecture notes. For example, in general, Fx could be like Eax. Fx could be cosine Ax, or Fx is sine Ax, kind of like this, or capital A, just independent of the A I used, or Ax, no, Ax, no, APXP, no, AN minus 1, XN minus 1, like A1X plus A0, or EAX cosine BX, EAX sine BX. Like this, you have to remember the table. I will not repeat it here because even though I tell you, you cannot remember, you just do problems and then after use it, and then you can memorize it. Okay, but you have to be careful. Sometimes, if, for example, the A is the same as the eigenvalue, you have to change it a little bit. So let us do the problems. Okay, if you have any problem, you just ask me because the case is complicated. Okay, so that's what I want to say today. Sorry, I made a mistake. I remember the date wrong.